Alright, last time we managed to set up the swap chain in the kind of simplest possible way. There's one thing that I initially missed with the present modes though, so I'm using the mailbox here. But the thing is that the spec actually only guarantees the FIFO mode, so first in first out, queue mode, to be there, and for everything else we should actually check if it's supported. So let's quickly do basically the same thing as we do for the surface formats and check for the supported present modes. So let's set the initial value to the FIFO. Let's use it in the swap chain create info. Now we need to get the supported modes using this get physical device surface present modes KHR method, which is exactly like get physical device surface formats KHR method, so it follows the convention of calling it twice, right? So nothing new here. Physical device, surface, then we need a number of present modes that are supported. We allocate a temporary array of present modes, fill it with the second call, maybe move the initialization after getting the present modes, just like we do with surface formats, and then we loop over candidates, and if it's the mailbox, then we are done and we are using that instead of the default FIFO. Now let's zoom out and think for a bit how we intend to actually use the swap chain that we just created. So the basic idea is to draw each frame, we ask the swap chain for a free image and acquire it for ourselves. Next, we use that image to render the frame, basically as a render target. It can be direct color attachment or just a destination for final bleeding or maybe even some storage image binding processed by a compute shader or whatnot. But then, after we are done with our rendering, we submit the image back to the swap chain for presentation, and the presentation engine will deal with it according to the current present mode. And at some point, the image will be available for acquiring again. And in the meantime, we'll use the next free image for rendering the next frame, right? So this doesn't sound too complicated. However, remember that GPUs are highly parallel beasts, and the Vulkan API is designed to take a full advantage of that, which basically means that everything is parallel and there are very little guarantees on the order of operations, and we need to carefully set up synchronization to ensure that every resource access happens at correct time. Because, for example, we don't want to render to an image that is currently being presented, right? Or we don't want to present an image that is still rendering, and so on. And in my opinion, this is the hardest thing to get a hang of in Vulkan, and I'm pretty sure that even the smartest people make mistakes on a regular basis with that. So, while I'm definitely not one of the smartest, but I think I got at least some basic understanding of this stuff. So let's try setting up a basic rendering loop that uses the swap chain as I described before. So let's go to our main loop here and outline our rendering sequence. So first we call this acquire next image KHR procedure to get the image from the swap chain. Then imagine that we do some drawing commands that we're gonna do later, but just imagine them for now, and we submit those commands using this queue_submit procedure. That will submit all our commands that we prepared to the GPU. And after that, we return the image to the swap chain for presenting using the queue_present_KHR procedure call. So far so good, right? But the issue is that those procedure calls don't actually wait for the work to be done. They just tell the driver to submit the work to the GPU. So it's all asynchronous. So let's take a look at the signature of the acquire next image KHR procedure. And it looks a little bit intimidating because it introduces two things that we never talked about before, the semaphore and the fence. And those are so-called synchronization primitives. And in principle, they are actually quite simple. The idea is that some operation can wait for a semaphore before doing its work, and some other operation can signal that semaphore to unblock the first one, right? With this simple idea, we can introduce some ordering, or rather some dependencies, in our parallel world. So in our case, here, with the acquire next image KHR function, we can supply a semaphore that will be signaled when the image is actually ready to be used. Because even though, as far as the CPU is concerned, the function already returned the image, the presentation engine still might not be done with it. So we actually have to wait for the semaphore to be signaled before, well, accessing the image in any way. Now, if we want to submit some commands to the GPU to draw to this image, we obviously want to make sure that the image is actually ready to be drawn, right? So we can give the semaphore to this queueSubmit and make it wait for the semaphore before doing any work. So let's take a look at this submit info argument, and indeed you can specify wait semaphores here. But also you can specify the signal semaphores, and those are going to be signaled when the submitted work is done. And by the way, the third main thing in this structure is command buffers, which is the representation of the work that we submit, and we'll get to it later. Now the queuePresentKHR function also takes an info structure, and it also has a wait semaphores. So knowing that we only want to present image once the work is done that renders to that image, it makes sense to have a semaphore that is signaled by the work batch, so passed as a signal semaphore to the queueSubmit, and awaited by the queuePresentKHR, right? So here with two semaphores, we can ensure that the work begins when the image is actually really ready, and the presentation only happens after the work is really done. Does that make sense? I know it's confusing, but hopefully it makes some sense. So let's try setting up a real render loop using that knowledge, and we will explore more of it. So let's see, for acquiring the next image we need a device, we need the swap chain of course, we can specify the timeout, I believe it's in nanoseconds, to wait for the image to be available, and like if it's not available after this timeout, we will get a special error code, but for simplicity let's just block for the maximum amount of time. And now we need a semaphore, so let's just have some variable for it for now, something like this, acquire semaphore. Then we can also pass a fence. And a fence is something that I never really talked about, but basically it's kind of like a semaphore, but the semaphores are normally awaited by the GPU operations, like the submitting or presenting. However, a fence is like a semaphore that can be awaited and reset by the CPU. And this is useful for signaling to the CPU that the GPU work is done. We will definitely use this, but not in this case. For acquiring, we don't need a fence, so we can just pass 0 there. And finally, this function returns an image index, which is, well, an index of one of the swap chain images. And we will actually need this for both rendering and presentation. So let's store it in a local variable, just like this. And then this function returns a result. And if we take a look at the spec, unlike a lot of other Vulkan functions, the successful result is not just success. It can also be a timeout or not ready. So the VK timeout is when the timer runs out. We are keeping things simple. We are using the maximum timeout, so we are assuming that it will never run out. The VK not ready is when the timeout is 0, so we can actually check if the image is not ready. Then we have this suboptimal KHR and then out of date KHR. And ideally we should handle those two. They are described here. Basically suboptimal means that we can still draw a frame to this image, but it's not really match the surface properties. So we should probably recreate the swap chain after we draw. And out of date is when it's so bad that we cannot even draw. So we should definitely recreate the swap chain right away. For now, we will not care about this, but we will definitely have to care about this. So for now, let's just wrap this in a standard VK check and then add a to-do, just like this, right? Now, how do we create a semaphore? Well, we created basically as any Vulkan object with a create function. So let's do it here for now. I will not extract this into a procedure for now because I consider this code still to be explorational, because there is actually more to the whole render loop, because we will get to having multiple frames in flight and stuff like that, so the structure will change. But for now, let's just create a semaphore locally. So we introduce a local variable, we call the create semaphore procedure, we pass the device to it, we pass the create info as usual, then the allocation callbacks and the result pointer. nothing really unusual here. And the semaphore create info one is actually interesting because it's really empty. You need to specify the S type as usual, but it only has the pnext and the flags that is an empty set, so you can't have any flags. So this is just reserved for the future. So this is all we need to have a semaphore create information. Good. This will give us an image that is almost ready and the semaphore that will be signaled when it's actually really ready. Now let's still imagine that we record some work for the GPU and then we submit it. And we do this with this queueSubmit call, right? Here we pass the queue to which we submit the work, and we have just one queue, so it's our GQ. Then we have just one submission, so the submit count is 1. And then for the array of submissions, we can just pass a pointer to a single submit info that we're gonna define. And the fence is something that we will talk about a little bit later. Wrap this call in standard VK check. This one only has a normal success condition. And let's fill out the submit info structure. So as I mentioned, we can pass a semaphores to wait before doing any work. So let's do that. We have our acquired semaphore here, and it's just 1. So we can also have a count of 1 and a pointer to the semaphore as our kind of array, right? So that's simple. But you see there's another field here, the wait destination stage mask. So here we need to specify the number of stage flags for each semaphore that we specify here, right? But because we specify just one semaphore, we can just pass a pointer to the stage flags value. So what are those stage flags actually? Let's see. As you probably know, with the GPU work, there are multiple pipelines. There is the most interesting one, the graphics pipeline, that draws pixels on the images. And then there's also a compute pipeline and a transfer pipeline. And some commands like the draw call, they go through the graphics pipeline, and it goes through all this vertex shader, tessellation shader, geometry shader, and then some tests, and then finally to the color attachment output, right? And theoretically, the GPU can actually start doing some vertex processing even before the image is fully acquired, because we actually are only drawing to the image in the color attachment output stage, which is after the vertex processing and whatnot, right? In practice, I don't think that's that easy, so I think that the commands will be just waiting for the semaphore right away. But still, it might be a good idea to specify here the precise stage at which our commands should stop and wait for the image. So let's do that. Just like this, we need a local variable because we need to pass a pointer to the submit info, like this, right? So next we would supply the command buffers containing the actual work, but for now we are ignoring this. We are interested in the signal semaphores. So the signal semaphores, as I said, will be signaled when the work is done. In our case, it will be almost immediately, right? Because we don't have any work. And this is where it gets a little bit tricky and a little bit confusing, but let's maybe explore this step by step and start by just creating another semaphore for signaling when the work is done. So just like this, I just created a second semaphore that is supposed to be signaled when the image is released. You know, when the work is done, we are releasing the image for presenting. So let's add it to the signal semaphores here, just like this. And now what we want to do is queue the image presentation and make it wait for this release semaphore to be signaled, because we want to present the fully rendered image. So let's take a look. That takes a queue. Again, we have just one queue, but in theory we could have a separate queue for presentation, but we will of course use our GQ, and then it needs a present info kchar. And let's take a look. So that takes also wait semaphores, and we want to wait for the release semaphore, as I told before. And then we specify a number of swap chain and the image indices for each swap chain as an array for presenting, right? And we just have one swap chain, so we will specify the swap chain count as 1, and we will simply put a pointer to the, well, the first and the only swap chain and the first and the only image index, which we just acquired. And the speed results field is for handling the presentation result for each swap chain separately. But since we have just one, we don't need that. We can just check for the VK result of the queuePresent call. So we set the swap chain count to 1, put a pointer to our swap chain as the first element, put a pointer to our acquired image index as the first element in p-image indices, and that looks almost good. Now the problem with all this is that there is no waiting whatsoever on the CPU side, so on every loop we are gonna acquire an image, then we do some work, right? And then we immediately present this work, and then without any kind of wait, we proceed to the next frame. And it might happen that the image from the last frame still haven't been even acquired yet, right? So it's been waited for the submit info, and we are already trying to acquire the next image, and we are using the same semaphore. And this is something that we cannot do because we can only use the semaphore for one cycle of wait and signal, right? We would need multiple semaphores, and this is something that we are gonna do later, actually. But for now, let's actually make our main loop wait for the submitted work to be done. And technically, we should probably wait for the image to be fully presented here in the queuePresent, right? But if we take another look at the present info KHR, unfortunately, there's no semaphores or fences that you could specify to actually wait for the presentation to be complete. Now, nowadays, there is an extension for that. I think it's called Swap Chain Maintenance 1 or something along those lines. But last time I checked, it's still not very widely supported, so it's not really safe to use. So we'll have to think of some other way. And what we can at least do is supply a fence here in the queue submit, right? If we remember, the fence is like a semaphore that can be awaited on the CPU side, right? So what we can do is create a fence that we will wait before doing any rendering, and it will be signaled by the GPU once the submitted work is done, right? So that will signal us that we can proceed with the next frame. So this is what I'm gonna do. And creating a fence is really similar to creating a semaphore, actually. So let's do that. Let's have a local variable like frame fence. Let's call a create fence function, pass the device to it, pass the pointer to the create info, as usual, the allocation callbacks, and the pointer to the result. Now the fence create info actually has a useful flag called signaled. And that means that this fence will be created in a signal state, which means that if we wait for it, we will immediately end the waiting, right? Because it's already signaled. And this is useful because what I plan to do is basically wait for this fence before doing anything else, then submit some work, and then pass this fence to the queue submit for it to be signaled when the work is done, so we can proceed with the next frame. Sounds like a plan, right? So we can wait for the fence with this wait for fences procedure, and as you can see, this wait for fences, it can wait for multiple fences. That does matter to us because we are waiting for just one fence. So we pass the device, we pass a fence count of 1, we pass a pointer to our frame fence as usual as a start of the fence array. Then this doesn't really matter, let's wait for all of them. And the timeout, for simplicity, let's also use the max uint64. So after the waiting is done, what we want to do is reset the fence, because the waiting will not automatically reset the fence, so it will stay in the signal state. Actually, unlike the semaphores, which are reset to the unsignal state once the wait is complete. With fences, we need to do this manually, so we have a similar function, a reset fences, that takes the device, the fence count, and the pointer to the fence array. Wrap this function in vkcheck as well. And now we can pass our fence into the queueSubmit call. So again, with these fences in place, our main loop will actually wait for the submitted work to be completed by the GPU before proceeding to the next frame. In future, we actually would like to already prepare the work for the next frame for the GPU while the GPU is working. So we will implement a kind of double buffering. Again, but this time not for the swap chain presentation, but rather for the GPU work preparation. So we do not stall the CPU while GPU is working. But even what we have here is still not quite ideal. Unfortunately, this single release semaphore is actually not enough. And if we run our application, we will actually see a bunch of errors, and some of them are expected, like this one, for example, that the image must be in the present source layout. This is something that we just never got to yet, but this one is interesting. You see, it says that the semaphore that we pass to the submit signal still might be in use by the swap chain. This suggests a problem with our synchronization setup, so let's analyze it a little bit. So at the very first frame, we're gonna have a signaled fence, so the wait will exit immediately. We will set the fence to the unsignaled to block the next frame. Then we acquire the next image that will give us an image index and the semaphore that will be signaled when the image is fully acquired, right? Then we submit some work that will wait for image acquisition with this acquire semaphore. And when the work is done, it will signal the release semaphore and also the frame fence, right? Then there is a present operation in the queue that will actually wait for the release semaphore before doing the actual presenting. And right after queuing all these operations, the CPU will proceed to the next frame, and until the work for the previous frame is done on the GPU side, the fence will not be signaled, so this wait for fences will block, right? And we are gonna wait. Once the previous frame rendering is done, the fence will be signaled, so we will proceed to acquiring the next image. And let's see, the acquire semaphore should be safe to use, because if the previous frame's work is done, then the waiting that this work was doing is also done, right? So it is safe to reuse the acquire semaphore. Now with the release signal semaphore, it's not so clear, right? Because even though the previous frame's rendering work is done, the presentation might not have been even started yet, right? Because it's still in the queue or something like this, right? So this release semaphore is actually might not be safe to reuse because it's still needed for the previous frame presentation to be reacted to. This is how I understand it. Now, this is really a subtle synchronization issue that is very easy to miss, but nowadays we have this validation error, and also there is this article on the Vulkan website, and the solution that is proposed here is to have one release semaphore per swap chain image. So let's see why this would work. If this release semaphore would be not a global one, but specific to a particular swap chain image, then we would get one after we know the image index, right? So we would have some array of release semaphores, and we would take this release semaphore from this array using this image index, and basically just use it here and here, right? And why this would fix the issue? Well, the thing is, the acquire next image would only give us an image that is free, or kind of almost free, right? That is finishing presenting. Which means that if this image is already presented, then this wait is already complete, right? So the semaphore that is associated with this image is definitely available and free for reuse. And this is a very non-obvious and tricky, but also quite elegant solution to this issue. So let's actually just do this and see if the error goes away. So we need to have a slice of release semaphores, one for each swap chain image. But for that, we need to know the actual number of swap chain image that we have, right? And believe it or not, we don't really know that yet. Because if we go here into the create swap chain, what we specify here is the minimum image count. But the actual image count might be greater than that if the driver decides so. So how do we know the actual amount of image that were created for the swap chain? Well, thankfully, we have this get swap chain images KHR procedure that we were gonna use anyway. because we will need access to the images to actually draw to them later, right? But of course, this will also give us the count of the images. Also the actual array of images, right? Because this is yet another function that we need to call twice, first to get the count and then to fill the array, right? So that means that it's actually not enough to just represent a swap chain as just a handle to the Vulkan swap chain object, because in reality the swap chain consists of the handle, the images that are provided by the swap chain, and as we know now, we also need to store a release semaphore per each image. With that knowledge, let's maybe introduce a new structure to hold all this swap chain information. So we move this handle into swap chain, maybe rename it to handle or something. Then let's already go ahead a little bit and create a slice of swap chain images. So the type for that would be simply a VK image. Let's also have a slice of semaphores. I'm not sure how to call it, maybe image ready semaphores or something like that, right? And now in our global structure, let's have a swap chain field of our new type. So now in the create swap chain procedure, we want to store the handle in the handle field, obviously. Now we want to get an actual image count. We already have a local image count variable, so we might as well reuse it for the get swap chain images kchar call. So that needs a device, the swap chain handle. We store it in image count, specify nil for the actual array for now, wrap it in VK check, allocate a persistent slice of images because this is what we are gonna use while the application is running, fill the data of that slice with the actual images, and now we just need to create all the semaphores for the number of images that we have just got from the swap chain. So we can just copy paste the semaphore create info, allocate a slice of semaphores, fixed assignment, of course, it's not a local variable. And then we just create the semaphores using the semaphore create info, which maybe we should move here, and store each of the created semaphore in our slice, right? Makes sense, hopefully. Now let's fix the destruction. We need to pass the handle to the destroy swap chain kchar. We do not need to manually destroy the images of the swap chain because they are owned by the swap chain itself, so they will be handled by the destroy swap chain call. But we of course need to destroy the semaphores and deallocate our slices, right? So this is what we are gonna do. Simply deallocate the images slice, destroy the semaphore using the standard argument structure, so device, the semaphore and the allocators for every of the semaphores that we created, and free the slice. Now let's go back to our rendering loop. So I removed our release semaphore creation from here. Let's fix the handle like this. And finally, the only thing that we need to do is get the release semaphore from our release semaphore using the image index, right? So we get the semaphore that is specific to this particular swap chain image, like this, right? Fix the handle here as well. And that should be it. Let's run the application and see if the error is gone. So here are the errors. And now we only see the expected errors about the image layout, which we're gonna get to much later, but there are no synchronization errors, and everything seems to be correct. Now, I know this is probably still very confusing, because, well, synchronization is always very confusing. You might want to go through it again, read the code, try to imagine what is actually happening in your head, right, between the CPU and GPU, and who waits for who. But now I can actually see that we do not handle the result for the queuePresent, and this queuePresent procedure actually is really similar to the acquire next image kchar procedure in the sense that it can also return the suboptimal kchar and out of date kchar if the window was resized or the surface got invalid in some other way. So let's add the same to do here and also wrap the call in VK check. So as you can see, that's at least something. Now we have a black screen instead of white, but more important that we have some notion of a kind of proper render loop. It's still not perfect, as I mentioned, that Ideally, we shouldn't wait for the GPU before rendering the next frame, because we can spend the precious CPU time to prepare the commands for the next frame already, right? But yeah, I think that's enough for now, and this is something for later. And I'm quite tired already of this part, so stay tuned for the next one.